All right. So, this is so yapacağım onu pazartesi. Hı hı, evet. Evet, evet. Evet, öyle olur. So, we stated this result, which is just basically Green's theorem. Uh, you know, there is a nice, actually, way of seeing Green's theorem. So, let me write as a remark. Uh, so, plumber muslukçu değil mi? Tesisatçı plumber'dı değil mi? Hı. Okay. Şimdi suppose we have some region like this, and this is the normal vector, and this is the tangent vector. Tangent vector is just dx dy, and this was minus, what was it? dy minus dx. dy minus dx. Okay. And suppose that, fluid, some fluid is flowing, and we would like to learn how much liquid, we have inside this region. Yani bir sıvı akışı olduğunu düşünün. Biz buradan ne kadar sıvı geçtiğini görmek istiyoruz. And suppose that the velocity of the liquid flow is given via this vector, and let's say it has f xy and gxy. So this is the velocity vector of the fluid flow. Yani bir sıvı akışı var. Bu da hız vektörü onun. Biz şeyi öğrenmek istiyoruz. How much so şöyle diyeyim ya da okay. So let's, yani içeriden bu region içinde ne kadar sıvı birikiyor onu öğrenmek istiyoruz. Peki, we would like to know how much uh, uh, liquid uh, uh, we have in the region omega. Şimdi içeriye toplam giren so total, okay, amount of liquid that enters the region enters omega at time t is what? Şimdi ne kadar sıvı girdiğini nasıl ölçersiniz? Sıvının, right? We have the velocity of the liquid at this point is this much. It means what? This much, let's say, liter liquid goes in x direction every second. This is the velocity, and the flow of the y coordinate of the velocity of the liquid is g. If you want to know how much goes out, then you should take the inner product of v and n, right? Over the whole boundary. Why is that? Well, of course, no. This bu içeriye gireni değil de çıkanı şey yapar. I should maybe put minus, right? Because I should, if this is positive, then we are measuring how much liquid goes out. You see, if V is perpendicular to the normal vector, it means what? The liquid is moving along the boundary, but it is not going outside. That's why we are taking dot product. Okay, dot product gives us how much liquid is going out. Okay, and if it is negative, it means you know. So if V is like this, then the inner product is negative. So we are measuring how much liquid goes inside. Okay, so the correct thing is to put dot product here. So this is the amount of liquid that enters the region omega at time t in let's say liters per second. Değil mi? Her saniye ne kadar giriyor mesela. Değil mi? Bu da nedir? So this is just minus. V is just F dot G. This is D neydi bu? dy minus dx. So this is just minus evet. Eksi şey yapalım. Eksi g dx'ti. Bir eksi daha var. G dx eksi f dy. Değil mi? Yok. Nereden çıktı? Ha tamam. Tamam doğru. Ve bu neye eşit? Şimdi onu söyleyeceğim. Yani Green teoreminden bunun ne olduğunu biliyoruz ama biz zaten Green teoremini yapmak istiyoruz. So we know from the Green's theorem what this equals, but let's just do the same kind of reasoning to compute that amount of liquid that goes inside. Now let me draw the region one more time. Suppose at a point like this, or I divide this region into small pieces like this. The total amount of liquid that, or maybe I should say it this way, the change, instantaneous change of liquid at any time, which is this, right? Bu her saniye içeriye ne kadar sıvı girdiğini gösteriyor. So this is the total, this is the instantaneous change in the volume that enters inside the region at time t, right? For any second. Well, actually our flow is time independent, so I should Yani T yok aslında burada da. Okay. Our flow is constant flow depending on time. I mean, it is time independent. So, but every second, this much liquid goes inside the region. How can I compute that number in a different way? I can compute it this way. Okay, suppose I just put, little pools here with base this much. So we have a pool like this. Yani küçük bir havuz gibi düşünün bunu. Tamam mı? Her birinde ne kadar su biriktiğini ölçersem, if I measure how much liquid, gathers in every little pool here and add them up, then I will learn how much, liquid we have, at any time inside this region. Yani her an buraya ne kadar girdiğini ölçersem, o zaman tüm region'a ne kadar girdiğini ölçebilirim. So if I measure how much liquid goes inside this every second and then add them up, then I will learn how much liquid goes inside this region. And how can you measure how much liquid goes inside this box here? Well, I have the velocity of the liquid. Velocity has two components, the x component and the y component. So let's say, okay, maybe I should write the x component, which is f, and the y component, let's say in this direction, g, y component. These are the components of the velocity. So to determine how much liquid goes inside this, we have to do what? I have to differentiate this with respect to x and this one with respect to y. Değil mi? Şöyle düşünün. Suppose I have two okay, so we have a pipe and then I have a meter here, and then we have this pool here, and then I have another meter here that measures how much goes out. So this is the, let's say, velocity of the water flowing in, and this is the velocity of the water flowing out. The difference is the amount that gathers in this pool, right? And so this is what you read here is F, right? This is F. F is this much here. It is this much here. Let's say here it is 90 and here it is 60. So the difference is 30, and we see that every second 30 liters of liquid gathers in this pool. And how do you so if you just have very small interval, how would you compare this to? Well, you just take derivative of this function along this direction, right? So that's why I just look at f sub x. I want to learn how much the velocity changes in this direction. It is f sub x, and how much the velocity changes in this direction. This is g sub y. Therefore, it is just f sub x plus g sub y. But our velocity vector is, okay, yeah, f plus f and g. So I have this. Therefore, I have to just add these things up. So we just multiply with dA, right, with the area element, and then integrate this. So that's equal to this gadget, g dx minus f dy. Green teorem bunun tam eksilisi mi olacak? Yani Green teoremde bu m n ise n sub x minus m sub y'dı. Ya bunun eksilisi oluyor. Okay, so I should. Ha zaten ama biz ona yani it is plus or minus depending on the orientations, okay? Ha bizimkinde zaten ben f ile g'yi böyle almıştım. Burada tersini aldık. O yüzden ikisi aynı çıkmalı. Tamam mı? Dolayısıyla bu hani Green teoreminin muslukçu versiyonu. Okay, so you measure how much liquid accumulates inside this region. Either you compute it locally at every point like this, or you just control the boundary. It is the other side of the problem. So it is over there. Okay. So this is just what? This is ne olmalı? Bunun eksi bunun y'ye göre türevi değil mi? Yok, x'e göre türevi eksi bunun y'ye göre türevi dA. Efendim? Ha, o zaman artı olacak burası tabii ki. Tamam. Evet. Ha işareti değiştirdiğimiz için şurası artı oluyor. O zaman şöyle. Ha. Tamam. Okey. Tamam. Neyse yani artı eksi çok önemli değil. Hani içerisi neresi, dışarısı neresi anlamına geliyor artı eksi. Neyse bu bir side remark about Green's theorem. Okay, now so let me just rewrite what we obtained over there. So we have okay. Şunu. So we have proved right for a region like this. So n ds, this is just dy minus dx, and we proved the following: integral along the boundary gradient of f n dot ds is equal to the integral of the Laplacian of f over dA. So the double integral of this expression. Now, as an application of this example, let's take f to be u times v where both u and v are some functions. Okay, C2 functions. So twice differentiable functions on the region omega. Then what is the gradient of f? So gradient of the product function. Well, we apply Leibniz rule, right? Product, so its derivative will be just v times derivative of the first guy plus u times the derivative of the second guy. This is true for all partial derivatives, therefore it is true for the gradient. Okay, now what about the second derivative? If you take Laplacian, so this is just f sub x plus f sub y. So if you just do this for u times v, you get the following. This is u times the gradient of v, sorry, Laplacian of v, plus v times the Laplacian of u, plus 2 times the inner product of the gradients of u and v. Bunları yani ispat etmiyorum. Bunları açıp yazarsanız doğrudan göreceğiniz şeyler. Yani işte gradient'ın ne olduğunu biliyoruz, değil mi? So gradient of f is just f sub x, f sub y. You just compute, these gadgets. This is what you will get. Peki bunu şimdi şeye uygulayalım. Bu sonuca. So let's apply this result to this f, okay? So we get what? Integral over the boundary, nabla f times nds is equal to what? This is just, this thing is this gadget. So this is just equal to integral over the boundary v times gradient of f inner product and ds plus u times evet. Tamam. Yok bu yok. V and up ds. Peki diğer tarafı ne? What about the other side? This right hand side. So this thing v u plus şöyle yazayım. Yok, şurası şöyle. This is equal to integral of the second derivative of f. So it is this gadget dA, but this is equal to what? This is equal to v times this plus u times this plus 2 times the inner product of this. Right? The whole thing is just integrated with respect to a. So we get this formula. Okay. Şimdi burada eee, şunu yaparsak let u equals v, then ne olacak burası? U'ya v eşit alırsak, so this is just 2 times integral over the boundary, right? These are both u, so I have u del u plus u del u, so I have 2 times u del u, and that's equal to integral. So this will be just u Laplacian of u plus u Laplacian of u. So I have 2 times u times Laplacian of u plus this is just 2 times del u inner product with itself, so norm squared dA. Okay, and if you cancel 2's, so you get just integral over the boundary of u nabla u is just double integral of u this plus, let me write it this way again, integral, double integral uh, nabla u squared dA. Şimdi bunları niye yazdık? Bunları da kullanacağız. Hmm. Ah, bir tane buraya bir şey yazmış ama onu anlamadım tam. Neyse, tamam, kalsın o. Okay. Ee, Böyle bir ah, neyse şöyle yazayım. Okay. Yeah, let's write Laplace's equation in polar coordinates. Bu çözümü elde etmek için kullanacağımız bir teknik için gerekecek. Şimdi polar koordinatlar neler? X equals R cos theta, right? Y equals R sin theta. Well, we have u as a function of x and y, so it is just also a function of r and theta because x is just r cos theta and r sin theta. Therefore, I can write u sub x and u sub y as derivatives with respect to r and theta. So, for example, what is u sub x? U sub x is just u sub r, and then, right, I can consider this as a function of r and theta, u sub r, and then del r, del theta, del x, ya da tersini mi yapsak? R'ye göre türevini x'ler y'ler cinsinden yazıp evet, şöyle yapmaya deneyeyim. Şöyle değil de. Yani aslında böyle de olur. Neyse böyle deneyeyim. Tamam. Plus u sub theta del theta del x, right? So what is u sub x x? Şimdi both of them are functions of x, so we have to use Leibniz rule. Derivative of u with respect to r, so u sub r r, and then derivative of r with respect to x. One more time, so this will be just d del r del x squared plus derivative of this gadget with respect to theta, so r theta, and then derivative of theta with respect to x, but I have also del r del x here. Değil mi? Doğru yaptık değil mi? Bu r'ye göre türevini aldım. Sonra işte çarptık. Sonra teta'ya göre türevini aldım, çarptım. Bir de ne yapacağız? And then u sub r and then derivative of this gadget with respect to r. So it is just del squared r del x squared. All right. Plus we have the same thing here. Derivative of this gadget with respect to r and then derivative of r with respect to x, and I have also derivative of theta with respect to x plus derivative of u with u theta with respect to theta, and then derivative of theta with respect to x, but I have already one term over here, and then plus u sub theta and then derivative of this gadget with respect to x, so del squared theta del x squared. So what is u sub xx then? Let me write one more time. U sub r del r del x squared plus, okay. So assuming that u is differentiable enough, derivative of u with respect to r theta is the same as derivative of u with respect to theta r. And here I have the same gadgets, right? These are the same, therefore we have just 2 times u sub r theta del r del x del theta del x plus this gadget u sub theta theta del theta del x squared, and then I have also these gadgets, so okay, u sub r del squared r del x squared plus u sub theta del sub theta del sub x squared. Okay. Şimdi bir de u sub y'da ne olacak belli değil mi? What about u sub y? So if I write here y, then all these x terms will be replaced by y, right? Therefore, this is just u sub x plus u sub y. So it will be just what? So I will have u sub r. I will have del r del x squared. No, del r del x squared plus del r del y squared, right? So this comes from this, and this product will come from that. And then we will have, okay. Yeah, so to u sub r theta, I will have, okay, del r del x, del theta del x plus del r del y, del r del, no, del theta del y. Okay, şuna gerek yok. Plus u sub theta theta, del theta del x squared, del theta del y squared, and then I will have u sub r del squared r del x squared plus del squared r del y squared plus u sub theta del squared theta del x squared plus del squared theta del y squared. All right, now we just need to compute all these derivatives. Okay, so let's do that. So r is just square root of x squared plus y squared, right? So I need all the derivatives. X'e göre türev, x'e göre ikinci türev, mix türev yok. İlginç. R, X, Y şekilde çıkmadı. Neyse. So what is R sub X? It is just X divided by the square root of X squared plus Y squared. R sub Y is just Y divided by X squared plus Y squared. What about R sub XX? Payın türevi 1 çarpı bu x kare artı y kare eksi x çarpı paydanın türevi, o da paydanın türevi 2x bölü bunun 2 katı, yani x kare bölü x kare artı y kare, sonra da paydanın karesi, yani x kare artı y kare. Dolayısıyla bu nedir? Şu şuraya gelecek. Bunun karesi olacak. Buradan x kare artı y kare eksi x kare. Dolayısıyla sadece y kare kalacak. Dolayısıyla bu y kare bölü x kare artı y karenin 3 bölü ikinci kuvveti. Alright. So what is r sub y? Well, it will be just x squared over x squared plus y squared 3/2. Yes. What else? Well, we also need to compute derivatives of theta. Theta is just tangent inverse y over x, right? Okay. So theta sub x is what? Okay. Bir de ikinci türevlerini alacağız, değil mi? Okay. Theta sub x. İçinin türevi eksi y bölü x kare bölü 1 artı y bölü x'in karesi. So it is just x kareler gidecek. Eksi y bölü x kare artı y kare. Right? What is theta sub y? Bu daha kolay. Orada yani y'ye göre türev olunca 1 bölü x bölü 1 artı y bölü x'in karesi. Buradan da x kareyi çarpacak. X bölü x kare artı y kare. Okey. Tamam değil mi? Evet, bunun doğru olması lazım. Y'ye göre türev alıyoruz. X kare ile çarptık. Tamam. So what is theta x minus y times bunun eksi birinci kuvvetini alıyoruz aslında. Eksi birinci kuvvetini aldığımız için eksi 1 ile çarpılıyor. Bu y eksi birinci kuvvetini aldık. İçinin türevi 2x bölü ondan sonra karesi. Değil mi? So what is theta y? Okay. O da aynısı olacak. Ama muhtemelen eksi olacak. 2xy x squared plus y squared. Okay. All right. So let's write down Laplace equation. Biri silmememde bir sakınca yok değil mi? Sonra ağlamayalım. Okay. So Laplace equation del squared u, so u sub xx plus u sub yy is equal to, well, what is this? Del squared x del r del x squared plus del r del y squared. Yani şununla şunun karesini topluyorum. So square of this x squared over x squared plus y squared over x squared plus y squared. So this whole thing is just 1, right? This is just 1. Şu da 1 mi acaba? Del x delta so theta sub x squared plus theta sub y squared. So that's also 1. Hangisi? Pardon. Şurası 1 bölü x kare artı y kare, yani 1 bölü r kare oldu. İlk terim 1 ama bunda sıkıntı yok. Yo, orada da var. Nerede? Dur. Pardon. Orada yok. Onlar karekök. Okay. So coefficient of u sub r is just 1. So u sub r plus coefficient of u what? Theta is 1 over x squared plus y squared. So it is 1 over r squared u sub theta plus, let's look at this one. This product plus this product. So r sub x times theta sub x. So this times this. So it is minus xy over something. And the other one is plus xy the same thing. So this term is just 0. Okay. So that is gone. Hepsini hesapladık. Bir tek bunlar kaldı. Second derivatives. This guy plus this guy. So when you add this two, you get r squared, x squared plus y squared divided by this. So we have only, so rx plus ryy is just 1 over x squared plus y squared square root. So it is just 1 over r. Değil mi? Öbürü de, so the sum of these two is just 0. Okay. Yani ne elde ettik? Okay. So this is 0. This is 1 over r. So 1 over r u sub r. Okay. So this is the Laplace equation in polar coordinates. Oops. Okay, let's stop.